Okay, so this topic is all about energy and work. And we're going to start off with work. So work equals force times distance. Okay. If it doesn't move in a distance, then no work has been done. And remember the work-energy theorem and the fact that work can change energy in a system. So since work can change energy in a system, work is kind of synonymous with energy. Okay. They're very similar. And sometimes you may see work in an equation. I may ask you something about energy. You can substitute energy in for that work. Now, a typical question for work might be something like, you apply a force of 30 newtons to push a box 5 meters. Okay? So force times distance, 30 newtons, times the 5 meters, we get work of 150 joules. Because it's synonymous with energy, our units are the same as energy. Now, other times you might get something acting vertically. Well, they might say that, a force of, well, let's do something different. Let's say that a box is moving vertically, let's say a 10 kilogram box is moving vertically at a constant speed. So the constant speed means that the force upward is equal to the force downward from gravity. Okay? And let's say it raises up 5 meters. So then let's say how much work is done. So in order to find out how much work is done, you would do work equals force times distance. Okay? But in this case, the force that's applied to move that object a distance upward 5 meters is equal to that force of gravity. So it would just be mgd. So 10 kilograms times 9.8 meters per second squared times that 5 meters. And that comes out to be roughly 500 joules. Okay. Now another thing that we can do with work is then find the power. And power is simply the work over the time. So let's say if we go back to, let's go back to this one. Okay. Let's say it was lifted those 5 meters in 2 seconds. So our work would be our 500 joules. Our time was 2 seconds. So that means our power is 250, and it can be a joule per second, if you don't remember what the units of power are, or 250 watts. Okay. Now this power is a little bit different than electrical power. We'll get to electrical power when we get to the electricity unit. Now, knowing that work can change the amount of energy, we need to take a look at the different types of energy that we studied this year. Okay, let's just draw a little chart to help us out. We had some kinetic energy. We had some gravitational potential energy. And we had potential energy stored in a spring. Okay, those are our basic ones. And the kinetic energy is due to motion. Okay? And the equation for kinetic energy is 1/2 mv squared. So 1/2 times the mass of the object times its velocity squared. And the units are joules. Or if you wanted to get fancy and you keep these units here, it could be a kilogram meter squared per second squared, and that's acceptable as well. Okay. Gravitational potential energy is due to an object's height or change in height. And the equation for that is mgh. And again, units are either joules or, again, it could be a Newton meter because this is a force and this is a height, so Newton meter is fine as well. Or it can be a kilogram meter squared per second squared. Potential energy in a spring. Okay. This is due to the distance the spring is either compressed or elongated. Okay. And our equation for that is 1/2 kx squared. And k is our spring constant, which has a unit of a Newton per meter, and x is the distance squared. Okay, the distance it was compressed or elongated. So again, joules or a Newton meter, or if you're really stuck, it can be, well, no, I guess that would be the same thing. So let's eliminate that. Okay. Now, any type of energy, any one of these can be converted into any one of the other ones, or into work. Okay? Energy is always conserved in a frictionless system. If there is friction involved, okay, if there is friction, this is important, some of that initial energy can turn into heat, or sometimes you'll see it referred to as internal energy. So it's still conserved, but it just might end up not as potential energy or gravitational potential energy or elastic potential energy or kinetic energy. It will turn into heat or internal energy. Now, mechanical energy is a fancy term for the sum of the potential and kinetic energy together. Okay? So if they're specifically asking for mechanical energy, they want to know the sum of the potential and the kinetic energy of the object at that position. And a good example of a conservation of energy problem might be something like you have a ball with a mass of 2 kilograms and it's 4 meters above the ground. How fast is it going before it hits the ground? Just before it hits the ground. Okay? And you can say that all that initial potential energy becomes kinetic energy as the ball falls, assuming this is an airless system, a frictionless system. So we have mgh on this side equals 1/2 mv squared. So these m's can cancel out. So we have gh, so 9.8 meters per second squared times 4 meters equals 1/2 times the velocity squared. Okay. So this side comes out to be roughly 40 multiplied by 2, you get 80. So the velocity would be the square root of that, so you're looking at roughly 9, a little less than 9 meters per second. Okay. But the mass is canceled out. That means that the mass has nothing to do with it as long as we're assuming that there's no air resistance. But this is a typical type of conservation of energy. Sure, you could probably use kinematics equations to find this, but this is a shortcut to using kinematics equations. You'd have to use multiple kinematics equations to come up with this exact same answer with one step. Okay. Another thing might be throwing a ball up in the air. So when a ball first leaves, let's just call this the ground, okay, it has the potential energy is at a minimum, and the kinetic energy would be at a max because it's going its fastest after it just leaves whatever caused it to travel upward. Okay? When it gets to the top, its potential energy is at a max because it's at its highest point. Kinetic energy would be at a minimum because for a brief second at the top, it stops moving. Because it's not moving, there is no kinetic energy. And on the way back down, it transforms back into minimum potential energy because it's closest to the ground, maximum kinetic energy because it's traveling the fastest. Another example would be a pendulum. Okay. If we draw this pendulum at a couple of various positions here, okay, the maximum potential energy of the pendulum would be where it's at its highest point, here. That would be max PE. At the bottom here, as the pendulum swings back down through, it's going to be traveling its fastest at the bottom. That's going to have max kinetic energy. Okay, so just a couple of quick examples there. You can also have problems where, like we did in class, where a ball rolls down a hill that's, let's just say, 2 meters tall, okay, and it hits a spring at the bottom. This has a spring constant of 100 newtons per meter. And let's say the ball has a mass of 1 kilogram. And we want to know how far is that spring compressed. So, oops, that would be an X, not a K, my fault. How far is that spring compressed? So we can use that initial potential energy, gravitational, equals stored elastic potential energy. So it would just be mgh equals 1/2 kx squared. Okay. So the mass would be 1 kilogram times gravity times 2 meters for the height equals 1/2 times 100 newtons per meter times x squared. So over on this side we'd have roughly 20 divided by 50 on the other side, so we're looking at 2/5, the square root of 2/5. Off the top of my head, I'm not positive. Where's my calculator? Okay, right around 0.63 meters. All right. So just another example of, one type of energy turning into another type. If you have any questions on any of this, don't hesitate to ask.